remind you what is valence electrons. So the valence electrons are the electrons that will be involved in the chemical bonds because they are located in the highest energy SMP subshells. Just remind you the subshell. So we have the main levels. Let me get my pen again over here. We have the main level that varies from 1 to 7 in your periodic table. So the rows indicate the level. So we have 1, 2, 3, 4, up to 7. And we have a sub-level. And each level, we have one or more sub-levels or sub-shell that normally we use letters instead of the numbers. So S is the 0. This is represent the shape of the orbital. So we have S, we have P, and we have D, and we have F that will be weirder than this. So it's the area that you can find that you have a high probability to find the electrons over there. Okay, so if you look to the chlorine over here, so in the first energy level, we have 2 electrons. That is the quantity, the maximum quantity that this first level can hold 2 electrons. Then you go to the second level that hold 8. And then you go to the third level that can also hold 8, but chlorine only have 17. So in the last level will be only 7 electrons over here, which means that this chlorine only needs 1 to be more stable. Why am I saying that? Because the element is trying to comply with the octet rule. And what is the octet rule? Octet rule, when the scientists look at the noble gas, they look at it like, why they are so stable? Why they don't tend to react? So this, when they notice, is like all the elements in the periodic table doesn't have a completely full shell and the last energy level. So that was like, probably this is the why the atoms tend to react with other atoms, because they want to achieve the octet rule. And why you call octet rule? So octet rule is because it's the tendency of main group atoms to form enough bonds to obtain 8 valence electrons. And you're going to say like, oh, okay, but helium only has 2. But this is the first and the last shell of energy this element has. And the first shell, as I said before, only holds 2 electrons. That means this shell is full. That will be the same with the hydrogen that I only have 1. So it tends to bond with another atom to have 2 electrons in the last shell. So it will be stable. Okay, this table in here means that they will spend less energy when they are bound compared to when they are separated, like by itself. Okay, so that's why the noble gases are so zen, so stable. So covalent bonds, so 2 atoms share electrons, occur between non-metal atoms. So when you look to your periodic table, you're going to see all those elements over here are non-metals, and when they interact with each other, they will form covalent bond. They will share electrons because they have like the last shell of energy almost full, very close to be stable. So they need just few electrons. So they have a high electronegativity. So they attract electron for itself. So they will share, they will not give away electrons. Okay. So when you see here the chlorine, so you can see they are sharing a pair of electrons. You can represent a pair by a dash. Okay. And the other electrons that are now non-bonding electrons, you need to show as the Lewis structure. 1 dot for each electron. Here I have 1 pair of electrons, 2 and 3 pairs of electrons. And if you count 2, 4, 6, and here I have 1 pair of electrons that will be count for both. So here I have 8, and here I have 8. So they are half and stable together. Okay. So here is the same thing. We have oxygen, and there we can have a double bond. or triple bonds, like nitrogen. Okay? They can share more than one electron, so they can have double or triple bond to achieve the octet rule. Electrons that are not shared by atoms are called bonding pairs. They are shared. They are bonding pairs, like over here and over here. And the ones that are alone, they are not bonding. They are called lone pairs, also known as non-bonding pairs. Okay? So here we have the bonding, a pair of covalent bond electrons, and here we have a lone pair of electrons. Let's look at those here. So in most covalent bonds, covalent molecules and polyatomic ions, all atoms follow the octet rule. For example, consider a CO2 molecule over here. In this molecule, the carbon atom form 4 bonds over here, right? And if you count, we have 1, 2, 3, 4, 5, 6, 7, 8. Because remember, each dash is one pair of electrons. So they are happy. If you go to the oxygen, I have 2, 4, 6, 8 electrons. And if you go the other one, it will be the same. Look at the water. Let's look at the water over here. So oxygen has 2, 4, 6, 8, and the hydrogen has 2 on each side. So they are happy and stable. Of course, we have some exceptions, and chemistry and life, we always have exceptions, right? Exceptions of the octet rule, we have the incomplete octet rule. So boron is a very humble atom and can be stable with less than 8 electrons in the last shell. Actually can be stable with 6. Another example could be beryllium. Beryllium can be stable. I will just connect you to atoms like the X over here. It's just a represent that we have an atom over there. So beryllium can be stable with just 4 electrons. So that is what we call incomplete octet. And also we have the expanded octet, because I'm pretty sure that you're asking yourself, okay, so we have atoms that can be half, like the humble atoms, that can be half with just a small quantity of electrons, like boron with 6 and beryllium with 4. Do we have some atoms that can be half just with more electrons? Yes, we do. That we call expanded octet. So like phosphorus, or all the elements and the rows or non-metals and the rows 3 to 6 can be happy with more than 8 electrons. Phosphorus can be happy with like 10, 12, doesn't matter. So remember that those elements in the row 3 to 6, we can have S, P, D. So remember that S can hold 2 electrons, P can hold 6 electrons, and the D can hold 10 electrons. That means that can be stable with 16, 18 electrons in the total, right? So phosphorus and other elements and the row 3 to 6, when you talk about nonmetals, can have expanded octet. Okay. And the important thing to draw the structure. So first thing is to remember how to check the valence electrons of each atom. Okay, look into the periodic table. If you go to group 17, all the elements will have 7 valence electrons. If you go down, like group 16, 6 valence electrons. 15, 5 valence electrons. 14, 4 valence electrons. 13, 3 valence electrons. Okay? So first we add up all the valence electrons. Remember, and the group 1, 1, and group 2, 2. We're not talking about the transitional metals over here. We're talking about nonmetals, metals, and noble gas. Okay? So then you frame the structure or draw the skeleton of the structure, which means draw the elements and connect all the elements together. And then you start distribute all the electrons that you have around, and then leave the central element for the last. Okay? Any remaining electrons on central atom, use double, triple bonds if needed. For example, here, let's draw a loose structure of nitrogen trichloride. So first thing, how many valence electrons nitrogen has? So go to the periodic table. See, nitrogen is located in the group 15, right? So it has 5 valence electrons. Chlorine is in the group 17. That means it has 7 valence electrons. So we have 3. So in the total, we're going to have 21 plus 5, 26 valence electrons. So first thing, draw the skeleton. The skeleton will contain all the elements, and you're going to connect all of those. And now you know that each dash contains 2 electrons. So now I use it already 2, 4, 6 electrons, but I still have 20 to go, right? Because it was 26 minus 6, 20 electrons to go. So we're going to distribute around. If I distribute around, I can make chlorine happy, and I'm going to add 6 for each chlorine. So now I have everybody happy, and we still have 2 that we put over here. Okay, so now we're going to count like 2, 4, 6, 8 for nitrogen, and 2, 4, 6, 8 for each chlorine. So they are all very happy. Okay, let's try this one. So first, let's do again. Look at your table. Carbon is in group 14, so we have 4 electrons. Carbon can make 4 bonds. And the hydrogen has 1 electron, and oxygen 6, but we have 2 hydrogen, so you add all together, and you're going to have 12 valence electrons. Let's look to this. This is the first skeleton, and I used 2, 4, 6 electrons already. So I only have 6 to go. And when I look to this, first I go around. So not to the center element, just around. So I go there, and again I put the electrons over here. So oxygen looks so happy. I can see, look, I can even imagine his face, like, yeah, 2, 4, 6, 8. But look at the carbon over here. Carbon is not happy because I have 2, 4, 6, and it also needs 8. So, okay, oxygen looks at carbon, so don't be sad. I can share with you this pair of electrons. And then this is what is going to happen. So, I'm sorry. So we're going to do is share this. And now we have everybody happy because now I have 2, 4, 6, 8 for oxygen. So we're still happy. And I have 2, 4, 6, 8 for carbon and 2 for each hydrogen. So everybody looks happy. Polyatomic ions. You need to take into account the negative or positive charge if you are constructing the structure, okay? Here we have some polyatomic ions that we have positive or negative charge. Okay? The distribution of this charge across the ions affected many of their chemical properties. Now that we have a better understanding of a covalent bonding, let's look at the structure of 8 common polyatomic ions over here. Most of these ions follow the octet rule, but 2 ions like sulfate and phosphate have expanded octet. So notice that each polyatomic ion has a here, just showing you the phosphate and sulfate here. Okay, formal charges are not a perfect indicator of the charge on an atom, but they are good total keeping track of the overall charge of a molecule or ion. So these charges that we're looking at are called formal charge. And this lesson, we will learn how to calculate the formal charge. Okay, a method to identify charged sites. Formal charge is an estimate of the total electron charge around bonded atoms. Formal charge assumes that atoms share electrons evenly. Since the 2 atoms share 2 electrons, each covalent bond contributes a charge equivalent to 1 electron. Let's look at this. So we're going to use this formula. Formal charge we're going to take into account valence electrons in the neutral atom minus number of covalent bonds minus the number of unshared electrons. So let's look to this example over here. How we're going to calculate this. So we have hydroxide over here. So hydrogen has 1 valence electrons and oxygen has 6 valence electrons. So I have 1 valence electrons minus 1 bond minus 0 because we don't have unshared electrons over here, right? So it will be 0. If you go to oxygen, so we have 6 valence electrons minus 1 bond minus 6, like 1, 2, 3, 4, 5, 6 valence electrons. So the charge is located in the oxygen over there. Okay. When you draw the list structure of the hydroxide, we commonly show the minus charge adjacent to the oxygen as shown here. Let's go to another one. Let's calculate this. So the charge, if you have hydronium, that's the hydronium, right? So, and we have a hydroxide over here. And then we have another element with the charge showing to you. And you don't have a located charge because we don't have 0. Let's calculate for, let's practice a little bit more over here. So automotive airbags contain sodium azide. The Lewis structure for this azide ion, without charge, is shown over here. Calculate the formal charge on each atom in the structure. What is the overall charge of the azide ion? So what do you need to know? Valence electrons, number of bonds, and number of electrons non-bonding. So let's go to the nitrogen, the center element. So valence electron is 5. And then we have the number of bonds, 4, right? I have 1, 2, 3, 4 bonds. And I don't have any non-bonding electrons around nitrogen. So we're going to have +1 charge, 5 minus 4. Let's go to the other nitrogen. So 5 is the valence electrons. I have 1, 2 bonds. And I have 1, 2, 3, 4 non-bonding electrons. So I have -1. So if you go to the nitrogen over here, you have -1 as well. Okay, so we have -1, -1, and +1. So azide ion is -1 because if you go -1, +1, -1, what are you going to have? -1. That is the charge of the azide ion. Okay, this is how we know. So similar to neutral molecules, the polyatomic ions consider charge when finding the number of valence electrons. Okay, so you have a +1, you're gonna decrease 1, so subtract 1 electron in the total. If you have a -1, you're gonna add 1 electron in the total of your valence electrons. So how many valence electrons are in hydroxide ion? So hydroxide ion is -1. I have oxygen with 6, and I have hydrogen with 1, but I have a negative charge, so I need to add 1 more. So in the total, I have 8 valence electrons. This is important. It's important because sometimes, mainly in exam, you probably will not take in consideration the negative or positive charge in an ion, but you should, okay? Let's practice. Draw a Lewis structure of nitride ion. So see, first thing that you need to know and remember, oh, at the end, I need to add 1 electron. So nitrogen has 5 valence electrons and oxygen 6 times 2 is 12 plus 5, 17 plus 1 will be 18, right? Valence electrons. Now you draw the skeleton. So NO2. Draw around all the electrons and the one remaining. But when you look to nitrogen, nitrogen is not happy because it has 1, 2, so 2, 4, 6 electrons. I need 2 more. So we can send a pair of electrons of each oxygen or of any oxygen because we have 2. So you can choose one and just share, forming one more bond. So we have a double bond over here. So 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons. 2, 4, 6, 8 electrons. Good? Everybody happy? So now if you calculate the formal charge, you're going to see what is the formal charge located at. So we can calculate here. Let's go and calculate here. So formal charge of oxygen will be 6 electrons minus 1 bonding minus 2, 4, 6 electrons, so minus 1, right? And if you go here, nitrogen is 5 minus 1, 2, 3 bonding minus 2 electrons, so 0. And here I have 6 valence electrons minus 1, 2 bonding minus 1, 2, 3, 4. So it will be 0 as well. So the charge is located in this oxygen. Let's go to another one. So the problem is asking what is the best structure for the phosphine. Important to know is we want a molecule, a structure with the lowest formal charge. If you see a molecule with a structure with formal charge like +2, +3, this is so high. You want to decrease that because the structure or the molecule will be in the form that spend lower energy. If you have a high, like a formal charge, they are spending a lot of energy. If you decrease the formal charge, they will decrease the energy expended. Okay, so what is the best structure here? We have there's a structure or that structure. Which one is the best? Here, what do you have here? Let's go to the formal chart. Let's calculate here. So now we're going to do on this. I have 6 valence electrons minus 2 bonds minus 4, so 0. If you go to this, I have 6 valence, oh, sorry. We'll erase that. That's chlorine, so it's 7, right? 7 valence electrons, and then we have 1 bond and minus 6, so it'll be 0. And then we have here 7, 2, 4, 6, but 1 bond minus 6 is 0. Everybody's 0. But when you look here, look at this. We have 1 charge. So 6 minus 1, right? Minus 6 is minus 1. Here we have 7 minus 2 minus 4. We have a plus 1, positive 1. And here it be 0, we already calculated. So we have a formal charge. This is all 0. So of course, the last one is the best one because we have low formal charge. Okay? Resonance. What is resonance? Resonance is when you have a double bond and they can move around. Remember, chemistry is about movement. The electrons are not freezing there, waiting for you to look at those. No, they are always in movement. And when they have a formal charge, they try to balance the formal charge, to reduce the charge on the elements over there. So the only way to reduce is to moving around. So the double bond can be on this side or could be in this side. And the way to represent that correctly is this, because that it's not only one structure that we represent this annual 2. Could be this or could be this. But it's not only one that we represent this molecule. So the correct way is to represent with dots over here, like a trace lines over here, that shows that the double bond can be on each side, like any side, okay? Or like this. Heteroresonance. So a set of structures that show how electrons are distributed and used when a single Lewis structure is insufficient. Remember, it's not only one structure that can represent that molecule, So we have more than one because the double bond can move around. That we call resonance. Probably you have seen this benzene. So can be the double bond here, or the double bond could be over here, here, and here. So the correct way to represent, and some books you're gonna see like this, the ring inside of the single accent. So that is the benzene. Okay. So they are distributing the formal charge over there. So ions of resonance structure, we have nitrate, NO2, PO4, SO4. They have a bunch of structure that can move around that we have resonance. See, you have the same elements attached to the phosphorus and the 4 equal elements, but the double bond can move around. Okay? You could represent another way with the trace lines. Okay, only second bonds are lone pairs, chain resonance structure. Okay? Let's go to this. Use a resonance structure to calculate formal charge. So the nitrite ion has 3 major resonance structure. Draw each structure. Based on this structure, what is the average charge on each oxygen atom? Let's look at this. So, and look at this. So you already know how to calculate the formal charge. We have 6 minus 2 minus 4 is 0, right? And carrying the double bond. And this that is not carrying the double bond is 6 minus 1 minus 6, so -1. And it will be the same for this one. So see, the charge is moving around. Now this is 0, now this is 0. Good? Charge on each oxygen is -1. But then if you have a 3 structure, so the sum of the charge, see the sum of the charge over here is 2, but then we divide by 3 because we have 1, 2, 3. Yeah? Because we're talking about the oxygen, not the sum of all the atoms, just about the oxygen. Okay. So shapes of molecules. As us, the molecules are things, right? They exist and they have different shapes. And why is that? So the shape of the molecules depends of the repulsion of electrons. Just to look at this, let me see. I'm going to use this pencil over here. Look at this. If I have, imagine it, I'm going to use only 2. Imagine that I have any element over here attached to 2 other atoms, 2 things. So around this center element, I have a pair of electrons that are non-bonding. And of course, all the atoms has electrons. So electrons are negative charge. What happens when you have 2 same charge codes? They repel each other, right? Right? Good, perfect. So if I have a charge over here, like electrons, non-pair, and we have atoms over here, what can happen? This will repel this, forming a band. If I don't have any pair of electrons around my central element, will not repel that. But those elements over here, those atoms, will repel each other. So the further away that it can be, like the furthest, like it will be the distance, the great distance between 2 atoms will be 180 degrees Celsius. So that will be the highest distance. So the shapes of molecules critically affect their properties as well. For example, when you breathe, what do you breathe? Our bodies expel 2 compounds, carbon dioxide and water. Drink water, please. Both are small, simple molecules, but CO2 is different. It's a gas at room temperature, and water is a liquid at room temperature. Why we have this difference? As we'll see in the lessons ahead, the shape of each molecule plays a big part in the to determining the properties of the elements, the compounds, okay? So CO2 is a linear molecule, while water is a band. Look at CO2. CO2 over here, can you see any lone pairs of electrons around carbon over here? No. So, but those electrons over here repel each other. That is the biggest distance between both, like 180 degrees. When you look to this other molecule, look at this. Why this has this shape over here? Because this will repel those electrons over here. So they need to be far away, okay? So we repel, forming this band structure. And look at this. We have CH4, okay? So the molecules will have the shape in accord to the number of atoms connect to the center element and the number of electrons. If you have a known bonding electrons around the center element, or if you have, that will be a big, huge difference in the shape. So that we call valence shell electron pair repulsion. So VSEPR. Let's look to electronic geometry that takes into consideration the electrons arrangement. So see, I have 2 pairs of electrons and 2 atoms, and in total we have 4. So we have tetrahedral. But when you look to the molecular geometry, we don't take into consideration the non-bonding electrons. You only take the atoms, the shape caused by the arrangement of the atoms, okay? So then we have here band shape. So linear, when you have it, doesn't matter if you have a double or single or triple bond, they will count only as one set, okay? Electronic geometry, it will be linear, and the molecular geometry will be linear as well, because you don't see a 0 non-bonding pair of electrons over there. Geometry stability. Which geometry is most stable over here? This, A, B, or C? Look at this. Look at the distance that we have. So first we need to consider the number of electron sets around the central atoms. Like our first example, this molecule has only 2 sets of electrons around the central carbon. Each double bond counts as one set. And so most stable arrangement is the one which keeps the electrons as far away as possible. So this will be far away as possible. That's the best one, 180 degrees, okay? So 2 sets of electrons, linear. If you have a 0 non-bonded pair. And you can have a trigonal planar, like this. It's trigonal planar because they are in the plane, okay? If you look like this, they are in the plane. So that when you have 3 things attached to the central element, 3 atoms attached to the central element, and the central element has 0 pair of electrons attached to them, like a free non-bonding pair. Then we're going to have a trigonal planar. Molecular geometry and electronic geometry will be the same. But sometimes we have a non-bonding pair, like here. Then we're going to have the electronic trigonal planar, and the molecular geometry will be band. So pay attention on that. Okay? And we have a tetrahedral. Tetrahedral, when they have one element attached to 4 other atoms. Okay? And will be not 90 degrees between the atoms. We can have much more space between those. So we're going to have something like this. Okay, so they'll be far away as possible, like 109.5 degrees. And we have electronic tetrahedral and molecular geometry tetrahedral as well. And we can represent like a tridimensional molecule. The dash means that the hydrogen is in the back, and the full here will be there in the front. Okay. When you have here tetrahedral electronic geometry, because we are taking consideration the electrons as well. But if you are not taking consideration these electrons over there, just the atoms, we have the molecular geometry trigonal pyramidal. Like here, water has 4, right? So we have tetrahedral electronic, and here we have band. So it's important to know bonding sets. You have the 2 zero-line pairs, linear, 3 zero-line pairs, trigonoplanar, 2 atoms, bond sets, 2 bonds, and 1 lone pairs. We're gonna have a band like this. If you have 4 bonding sets, we have tetrahedral. 3, we have 1 lone pairs, trigonopyramidal, and we have 2, but we have 2 lone pairs like water, so we have a band. Okay, so in this huge molecule, we have a trigonoplanar and tetrahedral. The atoms highlighted with green triangles have a trigonoplanar geometry, since they are each surrounded by 3 sets of electrons. Those highlighted in yellow have a tetrahedral geometry because they have 4 sets of electrons attached to them. Notice that outer atoms, those only connect to one other atom, have not been highlighted. Only the central atoms affect the geometry of the molecule, okay? Let's practice a little bit more. Lithium carbonate is a simple ionic compound that is widely used to treat bipolar disorder. What is the molecular geometry of the carbonate ion? So let's draw that. CO3. But we need the lithium carbonate. So we have electronic geometry of the carbonate, trigonoplanar, and the molecular geometry, trigonoplanar. Polar covalent bond. That is important. Atoms don't share the electrons evenly. So if you have 2 equal atoms, we're gonna have a non-polar, like here, hydrogen and hydrogen. But if you have different atoms, we gonna have a different electronegativity. So if fluorine has more electronegativity, electronegative than hydrogen, it will attract the electrons for each side. So with a B like this, the cloud of electrons will be bigger and the fluorine, so forming a partial negative charge. And we use delta to represent, and the cross arrow to show that electrons will be more and the fluorine because they're more electronegative than hydrogen. So when we have, how are we going to know? We have the periodic table of Linus Pauling that has the electronegativity for each element over here. Remember, electronegative increase left from right and decrease from up to down. So the extent that a bond is polarized is determined by the electronegativity of the atoms, is how they attract the electrons for itself. Okay? It's really important to understand the and remember that electronegativity is a measure of how strongly atoms pull bonded electrons. So increase left to right or down to up. Okay? Look to iodine over here, and bromine, and chlorine, fluorine. They are increasing. Okay? If you look at some elements like cesium and francium, they have the same electronegativity, like barium, radium also has the same electronegativity. Okay? Notice that this table does include the noble gas, and you're asking why? Because electronegativity is a measure of how strongly atoms pull electrons in a bond, right? Since noble gas generally don't form compounds, they don't have electronegativity values. Let's compare polar, covalent, and ionic. Look at sodium and fluorine. So a metal and no metal, we have ionic, right? And look two fluorines together, or HF. So look at this. If you have the difference in atoms of electronegativity lower than 0.5, we have a pure covalent bond. If you have values between 0.5 and 2, we have a polar covalent. Bigger than that, we have ionic. Okay? Analogy over here. Two dogs are pulling a rope. The big dog on the right has a much stronger grip on the rope. He could take it if he wants to, and he keeps the rope close to him. Similarly, in a polar covalent bond, like a HF bond, shown here, the electrons are held more in the side of fluorine, right? Let's look to this. Which bond is more polar? CO bond or FS? And please show the direction of polarity. Look at this. First, you're going to go to carbon and the oxygen. So carbon 2.5, oxygen 3.5. The difference of the electronegativity is 1. If you go to FS, you're going to see the difference is 1.5. Both are polar covalent, but a FS will be more polar. Okay? That's CO. And how are you going to show this? We're going to use the cross arrow pointing to the most electronegative element over here. And you can show the charge, like the delta negative shows that oxygen is pulling the electrons for its side, and the other case, fluorine is pulling the electrons for its side. Molecular dipole and overall polarity in the molecule, not dipole and dipole. So polar covalent bonds have a tremendous impact on the molecule properties. Molecules with polar covalent bonds often exhibit an overall polarity, called molecular or molecular dipole. Sometimes call it a net dipole or simple dipole. A molecule with a dipole has one side with a slight positive charge and one side with negative charge. We already talked about that on the slide before. So water, for example, it's polar and it's easy to see the charges over here. And I don't find my pen. Let me just, oh, it's here. So with here have positive charge because they are attracting the electrons, because oxygen has more electronegativity. It's more electronegative than hydrogen, right? And also we have those electrons over here. So we have more area electrons over there. So huge area compared to the hydrogen, okay? So oxygen side of the molecule has a slight negative charge, while the hydrogen has a slight positive charge. Look at this. Let's go to this. So CO2 molecule also contains polar covalent bonds. However, the molecule has a linear geometry, so the two polar covalent bonds pull opposite direction. As a result, the molecule has no net dipole. Okay, remember, some books will represent also like this. So we have this, like this. If difference in 0, that is net dipole, or the mu is equal 0, so we have no net dipole. That is the way to represent that. So you can see they are in opposite direction, so they cancel each other. In the linear position, we have no electrons that are non-bound in the central element, so that is non-polar molecule. So that is the difference. You need to pay attention to that. So we can have polar bondings, but a non-polar molecule. And here we have polar bonding, and also we have a polar molecule, okay? And this is very important when you talk about solubility. So remember that equal dissolves equal. Polar will dissolve polar, non-polar will dissolve non-polar, okay? Let's look again to the other molecules. Look at SO3. So their pool oxygen has more electronegativity than sulfur, and there's also the sulfur. And we have the net dipole over here because they are pulling the opposite direction, but we have electrons over here that are non-bonding, okay? Because they are not actually pulling in the opposite direction, because we have like a band shape over here, not linear like the CO2 before we had. So in the moment that we have a non-bonding electrons in the central element, our molecule will not be linear. And things even think that you could think like, oh, they are in the opposite direction. They are not, because they are in band shape. Okay, so this is similar to two tractors trying to pull a stem out of the ground. If the tractors pull in the direction of the red arrow, their combined force pull the stem in the direction of the blue arrow, right? So here, the net pull over here, okay? Because they are in different directions over there, right? So just remember that. The easy way is, okay, I have three elements, two things attached to the central element, and but we have non-bonding electrons around the center. That will be net dipole, will be a polar molecule, okay? Look at those. Which one have a net dipole? First, let's draw. We have a non-polar molecule here, because they will attract the electrons in the opposite directions. We have no dipole. All the hydrocarbons, which are molecules with carbon and hydrogen, are no polar molecule, okay? There's one over here. So then we have a symmetry, 1, 2, 3. So we have over here polar bonds, but look at this. We have a result force over here. We have it together. Oh my God, over here. So they're in opposite direction, and then we're gonna have no net dipole, so a non-polar molecule. And here we have polar bonds, and we have a net dipole. So if you have all the atoms equal and you have a symmetry, we have a no dipole. If you have like a boron trichloride over here, we have like a force resultant over here. So this cancel out with each, and this has symmetry. They are all the same element, so we have no net dipole. And also here we have no net dipole, or actually we have net dipole because we have different elements, different force. Okay, it's important. So let's get back on this. The shape and polarity of molecules impact their behavior, as I said. Let's compare the properties of CO2 and water. So we have CO2, it's linear, and it has no net dipole, because in linear they put in the opposite direction. And we have water that is bent, and we have a net dipole. Remember, water, we have electrons, non-bonding electrons around the oxygen over here. So we have a moment dipole different than 0, so we have a net dipole. Okay? So when you look to the water, water is liquid, 25 degrees Celsius, while CO2 is gas. So here we have a net dipole, and here we don't have net dipole, okay? Because the molecules here in the CO2, they don't stick together as tightly as water do. So in the chapter ahead, we'll explore these ideas in much more deep details and see how the shape and the polarity will determine how they interact with their surrounding. So that's it. That's all. Have a great day.